All right. So thank you guys very much for participating in the trivia and getting your prizes. And so now we'll move on to our second talk of the night. So for this talk, we have Dr. Humberto Campins from the University of Central Florida. He is a Pegasus professor of physics. And he's going to be talking to us tonight about planetary defense. Ooh. So take it away, Dr. Campins.
International collaboration for planetary defense. Thank you. It's a pleasure to be here. Boy, in-person contact. Wow, what a concept. It's been a while since I've seen many of you, and I've seen many of you for the first time tonight. So this is great. Thanks for the invite.
I'm sorry, I'm going to also ask you to put this on as well.
Okay. As well?
Yeah.
Okay.
That goes on.
Hold on.
Sorry.
Technical difficulties, my bad.
All right.
There we go.
And this.
And,
And what about the
can go in
pointer?
your pocket.
What about a pointer?
Pointer is... Yes, right here. See there?
I think you do it to the screen. No.
Huh? I did. There we go.
Okay. Thanks. Okay, so as Kenny said, I'm a professor at UCF, although I have not been here in Orlando very much recently because I was a Jefferson Science Fellow at the State Department for a number of months. And after that, I got my sabbatical. So I moved to Spain for a year, and then I moved back 2 months later. It's a long story. Anyway, so I've been involved with the OSIRIS-REx mission, but more importantly, I've been involved at the State Department with a lot of this international collaboration for planetary defense. So I'll tell you a little bit more about, I'll give you some examples of that. So I'll be telling you about asteroid impact hazards, give you two current collaborations, which are between OSIRIS-REx and the Hayabusa 2 mission that the Japanese successfully sent to another asteroid and brought back a sample. And then the recent DART impact on Didymos and then on Didymos and Dimorphos, the system, and the Lichia, I guess this doesn't point, the Lichia cube, which was riding piggyback on DART and took some images of the impact. Okay, so how likely is an asteroid to ruin your day? So do you look at asteroid forecast for tomorrow? And the answer is not very. So as individuals, we all don't have to worry about an asteroid impact because it is so unlikely to happen during our lifetimes. However, as a civilization, we must worry because large impacts have happened. For example, the one that killed the dinosaurs, and they will happen again unless we do something. So the dinosaurs did not have a planetary defense office, and but we do, right? And so one of the reasons for this office is because asteroid impacts can be eliminated or mitigated. It's the only natural disaster that can be completely eliminated or mitigated. So how do we protect our planets? First, we find the asteroids that are in hazardous orbits, like one of the trivia questions earlier. Most asteroids that can cause global devastations have already been cataloged, and they're not threatening us. However, potentially hazardous asteroids are those in orbits that are not threatening Earth now, but could evolve into an orbit that threatens Earth. And so both of the asteroids that were targets of sample return missions, OSIRIS-REx and Hayabusa 2, are potentially hazardous. So Bennu and Ryugu, a tale of two asteroids. These guys are both potentially hazardous, as I said. They're not an immediate threat, and they're in similar orbits, and I'll discuss a little bit about each of them. So NASA's Planetary Defense and Coordination Office includes international collaboration for planetary defense, and featured in the recent movie Don't Look Up, by the way. Bill Gates and Steve Jobs don't get along, never got along, so that's why this thing, which is being shown on a PC, doesn't show well. Anyway, how many of you saw Don't Look Up? All right, so we got a good, okay. Now, that was Hollywood. In reality, my colleagues at the Planetary Defense Office at NASA headquarters are much cooler than in the movie. They would not bring a professor from Michigan State and a grad student, no matter how attractive she is, they would not bring them to the White House. That's why they are Planetary Defense Officers. They would relay that to the White House. Anyway, I'll give you more details in a bit, but so Hayabusa 2 and OSIRIS-REx are collaborating in several ways, and I'll go into that. And then NASA's DART and Lucia Cube are complementary also. So OSIRIS-REx went to asteroid Bennu, picked up a sample. It's on its way back to Earth. We'll deliver that sample to the Utah desert in September of 23. Hayabusa 2 went to asteroid Ryugu, picked up 2 samples, and brought them back to Earth, and they're now being analyzed in laboratories. So, as I mentioned, these 2 asteroids have very similar orbits. Bennu has an orbit that comes barely within the Earth's orbit and then goes back about more than halfway to the orbit of Mars, has low inclination. Ryugu also has a similar orbit. It goes all the way to the orbit of Mars and comes slightly within the orbit of the Earth. And it's also low inclination. And I was giving this talk in Slovakia about 2 months ago, and somebody said from the audience, can you use Ryugu as a way to transport things between the Earth and Mars? And I had never thought of that. And the answer is yes, you can, if you're not in a hurry. Because it could take us as long as 10 years for the orbits to line up and for you to be able to deposit something on Ryugu when it's near the Earth and have it delivered to Mars. But it's a cheap transportation system. So here's Bennu, a series of images taken by OSIRIS-REx in December of 2018. And then here's Ryugu. Ryugu is about twice the diameter of Bennu. They look very similar. Their surfaces are both dark and primitive, but Ryugu is twice as large. Okay, so OSIRIS-REx. Since I am on the OSIRIS-REx science team, I can tell you a lot more about this mission, so I'll go into some detail about that. We have 4 main themes: revealing solar system history, mitigating impact hazards, enabling human exploration, and developing a space economy. So I'll go through them real quick. In terms of developing a space economy, that is let me back up for a second. So this is because we're bringing back a sample of a primitive asteroid, because Bennu is a potentially hazardous asteroid, because astronauts are likely to go to asteroids before they go to Mars, even if it is the moons of Mars where they stop on the way to the surface of Mars. And developing a space economy, I want to spend a little extra time on. And that's because the moment that you can mine from asteroids resources cheaper than you can put them into orbit, you're going to have a market for those resources, specifically water. Because if you can mine water and asteroids cheaper than you can put it into orbit, you can split it into hydrogen and oxygen, and that's fuel. And so you're going to have a market of all Earth orbiting satellite that would rather buy the fuel from you than to have it put into orbit. No matter how cheap things become, and they are becoming cheaper, still, once you can produce them cheaper from asteroids than to launch them, which is still very expensive, then you're going to have a self-sustaining space economy. In addition to that, imagine communication and other satellites being 3D printed in space with asteroid materials. Most of you are probably familiar with the James Webb Space Telescope. instead of taking that complex structure and folding it onto itself and putting it into a tube, shaking it, launching it, putting it up there, we could have, if we had the materials and the big enough 3D printer, 3D printed it up there. It would have been a lot cheaper and a lot faster than it was done when it was built here on Earth and then had to fold it into itself. And then imagine other structures. For example, if we wanted to have solar panels and collect solar energy to power either Earth orbiting platforms, and even beaming that energy back down to the Earth, you could 3D print very large structures that would not be possible to print on Earth and then launch. And even better, you don't have to print them, you don't have to build them to withstand 1G. You could build them for them to be stable at, in the environment that they will be up at 0G. Okay, so I was surprised when I was invited onto this team, which was in 2010, that this was going to be only the 4th time that NASA was going to be bringing back samples to Earth from outside the Earth. And the first time was the Apollo missions. You all know about that. Second time was Genesis, which brought back samples of the solar wind. The third time was the Stardust mission, which flew through the tail of a comet, brought back dust from the comet and interstellar particles. And OSIRIS-REx is only the 4th time. So this is also related to one of the quiz questions. Here are most of the asteroids in green, and the Trojan asteroids in blue, and the red dots are the near-Earth asteroids, right? And you're probably thinking, Dr. Campins, how come there's a near-Earth asteroid up near Jupiter? It has a very elliptical orbit, so it comes near the Earth. So at the time that I did this graph from the JPL website, that's where that asteroid happened to be. Okay. So these are asteroids that have been visited by spacecraft. So we have OSIRIS-REx that went to Bennu, Hayabusa, and Hayabusa 2 that went to Itokawa and Ryugu. So most of the predicted results from Bennu match the findings very well. So we were so pleased with ourselves. Everything that we predicted is coming true, and we were so smug. And so global properties, spin top shape, composition, spin rate, everything was turning out to be just like we had predicted for Bennu and Ryugu. These were the shapes that were, the shape models were done from ground-based observations, mostly radar, of both of these objects, and these were the images once we got there. So we were quite pleased, except that we expected areas of coarse sand or pebbles on the surface in order to be able to sample the surface. So basically we expected Daytona Beach, no rocks, sand, plenty of room for a spacecraft to come down, sample, no hazards, right? So coarse sand or pebbles, this guy is about 3 meters high, right? So nope. So we had to change drastically our descent strategy to avoid crashing into all those rocks. So we obtained detailed images of the surface, and we programmed the spacecraft, once it was already there, to descend autonomously, make its own decisions and course corrections, come down to the surface, pick up the sample, and get away safely. And initially, the navigation team wanted an area that was 150 feet across with no rocks for them to bring down the spacecraft safely before we did this. And when we first got there to the asteroid, well, this was our strategy to approach, which is what we actually did. But they needed an area that was 150 feet across, no rocks. So when we first got there, we told them, no such area. Okay, but the spacecraft is navigating so well, and the navigation team is so good, we can put it down in half that area, 75 feet. Bang, no such area. And so they go, how big? And we said, about 25 feet across, and with lots of rocks around it. And so that's when we decided, you know, that we needed a big change. And so I am illustrating this because we needed a very low vertical velocity and a very low horizontal velocity for us to, you know, come down to the area where we wanted to sample. And just to remind you, this asteroid was rotating every 4.3 hours. So the rotation velocity of the asteroid, we had to match, so not just the descent, but also move along with the asteroid. We were not in orbit around that time. The spacecraft was maneuvering constantly in order to be able to keep both of those velocities low. So we did that successfully. So these are images from October 21st, 2020. Went down to the surface and successfully fired the nitrogen bottles that were going to fluidize the dust and put it into our sample canister. And it turns out that we collected a lot more sample than the minimum threshold. The minimum threshold was 60 grams, and we're estimating that we collected 250 grams plus or minus 100. So we're looking forward to having lots of sample back. We quickly stowed that canister onto this capsule, which is the capsule that's going to deliver it to the surface of the Earth, because at one point we were going to measure exactly how much mass we had, because we had extended the sample arm and rotated the spacecraft before there was anything in the sample head, and then we're going to do that again when the sample head was full of the sample and be able to measure the mass quite accurately. However, when we imaged the canister, there were particles that were just brimming and drifting out away from it. And I remember Dante Loretta, the head of the mission, we were looking at the images, and he goes, there was a particle that was moving away, and it was going, there goes somebody's PhD thesis. And so the decision was made very quickly. Instead of measuring how much mass we had, we're going to stow, bring it back to Earth, and we'll measure it once we get here. We could estimate that 250 grams plus or minus 100 from how the mechanical arm responded as we were stowing it. Anyway, the other mission was Hayabusa 2, which was very successful. They not only went to this asteroid and picked up a sample, but they decided that was not enough. Why don't we throw a projectile onto the asteroid, create a crater, and go sample that crater too? So they did that. Their risk tolerance was a lot higher than that of NASA. So NASA and the Japanese Space Agency have agreed to share 10% of the sample. So we're going to give them 10% of our sample once we get it. But they have such confidence that we're going to get our sample. They already gave us the 10% of their sample. So the samples of Ryugu are already in American laboratories being analyzed. All right, so very quickly, let's talk about DART and Lucia Cube, which you probably know a lot about because it's so recent and so successful. So the double asteroid redirection test was sent by the Planetary Defense Office at NASA to hit asteroid Dimorphos. This is another tale of two asteroids. Dimorphos orbits Didymos. It's ideal for redirection tests. Dimorphos and Didymos are not hazardous asteroids, but they are ideal for this test so that we can not only demonstrate the concept on them and then in the future apply to any asteroid that could be threatening Earth. So NASA's DART impacted Dimorphos on September 26, and Lucia Cube recorded the impact. And we got some very interesting images. Here's another depiction of the spacecraft headed towards Dimorphos, and Lucia Cube having separated from it about a week and a half earlier and recording some images. The impact was a lot more successful than we had anticipated. They measured the difference in the orbit in a matter of 2 weeks, and we were able to image a lot of the material coming out. All right, so in conclusion, planetary defense against asteroid impacts benefits from extensive international collaboration. As a matter of fact, there's another European Space Agency mission called ERA, H-E-R-A, which will be launched in 2024, and it's going to go look at Dimorphos and Didymos in great detail. So it's going to do a crime scene investigation of the results of the impact by DART. OSIRIS-REx and Hayabusa 2 are exchanging samples, and DART and Lucia Cube tested a very important planetary defense technique. And that's it. Any questions?
Any questions for Dr. Campins? I think we have. There we go.
So you mentioned we had about 250 grams plus or minus 100 from Bennu, but how much was collected from Ryugu? Like a 5 grams?
So they're going to get a lot more from our 10% than they got from their entire sample. But hey, we don't mind.
Any other questions?
What's the most hazardous asteroid?
Actually, last I looked, it was Bennu. But it could be, I mean, their orbits are evolving, the new ones getting discovered. But last I looked, it was Bennu. Yeah. Which means it's also a great target for space mining. Because I'm sorry? The question was which is the most hazardous, the most potentially hazardous asteroid? And it's Bennu. So it's if we're going to mine an asteroid, Bennu is a really good candidate because we can get to it easily. So is Ryugu. Yeah. Phil.
So from the OSIRIS-REx mission, have you learned anything about the origin and evolution of that asteroid?
Yes, that's a very good question, and I don't think I have those slides in my presentation here, but we learned a lot. And one of the things that is particularly satisfying for me is that we discovered pieces of another asteroid on Bennu. And not just any other asteroid, but asteroid Vesta, which is the most unique and easiest to identify asteroid in the asteroid belt because of its lava surface. Well, there were pieces of Vesta on Bennu, which means it is very likely that when there were impacts on Vesta, some of those pieces ended up, dissipating through the inner belt and hitting the parent of Bennu, and pieces of it survive on the surface of Bennu. Now, I had, based on a meteorite called Almahata-Sitta, which fell in 2008 in Sudan, that meteorite had such diverse pieces that had to come from different asteroids, and because its orbit was somewhat similar to that of Bennu, and it had a similar origin, I predicted to the team that we should be expecting rocks on Bennu that came from another asteroid, and bright and dark pieces. And they told me, "Shoo, go away, forget it. That's such a low probability." They almost sent me to Guantanamo to be waterboarded. And so I just, well, all right. It's a large team. I'm in the minority. Turns out we get there, and the head of the imaging team, by the way, 4 people did take me seriously. The head of the imaging team, one of our colleagues from France, and the 2 people in the spectrograph, the PI and the deputy PI of the spectrograph. Anyway, we get there, and the head of the imaging team says, one day says, "Humberto, come here. Look at this." we found really bright rocks. We've identified 6 of them so far. And what do you think of this? And I said, it's what I predicted, right? And and then we talked to the people in the spectrograph, and they took spectra, and they turned out to be pyroxene, which is the mineral that you get when you melt an asteroid or a planet and it flows to the surface as lava. That's pyroxene. And it was pyroxene. Not only was it pyroxene, but it was a type of pyroxene that you could only find on the surface of this one unique asteroid, which is Vesta. So we published that in the journal Nature, and then we did a more detailed study that came out in Nature Astronomy, and we ended up finding 73 objects that were likely exogenous, in other words, didn't form when Bennu formed, and most of them from Vesta, but some of them also with the characteristics of what we call ordinary chondrites, which is a different type of meteorite that comes from the inner belt, and so it's likely from asteroid Flora. Anyway, so we've learned a lot, and that's just because we discovered exogenous material on Bennu. The other thing that I want to mention is that when we talked to theorists about the possibility that the projectile would survive the impact and would still be present on the surface of an asteroid, before we got to Bennu, the theorists all told us that it was completely impossible, to forget it, go work on another problem, you don't waste your time on this, right? And then we got there, and quickly the theorists said, oh, but if we tweak our models, you can do that. So now the theorists can predict what we discovered. Anyway, some of my best friends are theorists. All right, any other questions?
All right, so considering the inability to react quickly to a cometary impact, is there any, I don't know what the likelihood of a cometary impact versus an asteroid impact? It seems like this is pretty well, sorry. So the planetary defense appears to be concentrating on asteroid impact. From a likelihood perspective, is that more likely than a cometary impact, or do we know? And if not, what is being considered for a low, you got a low response time for a cometary impact, so just curious.
Yes, most of the hazard comes from asteroids. Comets do represent a small percentage of the hazards, and the consequences are much more severe if we do get hit by a comet, because the relative velocities are on average higher, right? And there's actually some work being done on defending on short notice from something like that. But most of the work is being done on defending from asteroids because they represent the large majority of the threat. Now, if you don't have an object that is large enough to create global devastation, but it's still a threat and you discover it early enough, you could have evacuation of a city, for example. So there's a whole range of mitigation depending on the threat, depending on how early you detect it. So the longer the time scale, the easier, because you need a lot smaller deflection for it to miss the Earth if you give it enough time. So the Europeans have a mission called the Comet Interceptor, where they're going to park it up there and wait for a particularly interesting comet, and so once it's going to be in orbit, and then once they choose the target, it's already going to be up there. It's going to head towards that comet and study it as a predecessor for something that would defend us against a comet impact. Yes.
My question was, how exactly does understanding the composition and properties of the surface help us be better prepared? Obviously just understanding the objects is important, but any details about how it helps us?
That's a very good question. For example, we had no idea how this asteroid was going to react to how we touched it. When we touched the asteroid, we had all kinds of sensors to determine how much it was going to push back. Had we not fired the thrusters, the whole spacecraft would have buried itself in the asteroid. It offered no no force. There was no reaction force whatsoever. So this thing is got essentially its coefficient of friction is 0, and we couldn't measure it. And so that we have to take into account if we try to deflect it. We need to figure out a way to deflect it that is not just pushing on it, or at least not pushing on it with a small spacecraft. There are all kinds of characteristics of both Bennu and Ryugu that we're going to be refining in case we do have to deflect them. So, for example, a solar sail could be an option, where you put a very large surface that reflects sunlight and slightly pushes the asteroid away. Or a gravity tractor, where you park another spacecraft or a spacecraft on an orbit next to it, and you nudge it slowly away from its original orbit from the gravity between the two. And there are actually ways of enhancing that, where the gravity tractor goes and picks up big boulders from the surface of the asteroid, and then uses that as mass to nudge it away. So, yes.
You talked about the DART mission. You talked about the DART mission impacting Dimorphos. Do we have a mass ejection estimate for what was ejected from that impact, or velocities or anything?
There are. I'm not. I don't know if they've been published yet, but yes, there were some quick estimates from the initial images, but I'm not aware exactly what the amounts are. But it was a lot more ejected than they expected, and a larger change in the orbit faster than they expected. So the energy that DART deposited must have gone into a very strong jet in the other direction, which changed the orbit. Oh, sorry.
So I've heard there are some plans for OSIRIS-REx and Apophis in October 23. I was wondering if you could say something about some of the specific science goals we have.
Now that's a good point. So the OSIRIS-REx team proposed, or a subset of the OSIRIS-REx team proposed to NASA to have an extended mission, and it was approved. So OSIRIS-REx, once it delivers the capsule to the Utah desert in September of next year, it will go into an orbit that will eventually bring it back to Earth in 2029, and it will join with Apophis, which is an asteroid that will come between the communication satellites and the surface of the atmosphere of the Earth. It's going to come really close. There's no chance of it hitting us. We know exactly its orbit, we know its size, and it's not going to hit us. But it's going to come between the communications, the geostationary satellites and the Earth. So once it goes through, OSIRIS-REx, the spacecraft is going to join it and spend several months studying it, and it will have a number of science questions, characterize an S-type asteroid in a lot more detail. Apophis is an S-type asteroid. Bennu was a D-type asteroid, and a B-type asteroid, like boy, and there are a number of interesting science questions, and also planetary defense questions. If we have to deflect Apophis, how much can we learn about orbiting it, measuring its mass distribution, and etc. And even though OSIRIS-REx won't be able to pick up a sample and bring it back to Earth from Apophis, it may be able to just nudge the surface. We can risk the spacecraft at that point because our main mission will have been completed. So who knows? Good question, thank you.
All right, any other questions? If not, let's thank Dr. Campins. And thank you all very much for coming out to the first ever Astronomy on Tap Orlando event. That concludes our event for tonight. So if you could, thank you very much. If you could, please fill out. I'm sorry? Oh, that does not conclude our event. We actually are also planning to set up some telescopes outside to potentially do some stargazing, depending on the weather. I'm not sure if it's cloudy.
You can use my shirt.
Say again? There are Jupiter, Saturn, and the Pleiades currently in view outside, so if you would like to go outside and do some stargazing now that the event and the talks are over, please do. And please feel free to fill out the feedback survey that's on the QR code on your table, and let us know how we did so we can keep improving for the next time. So thank you all very much for coming out.
Go Artemis.
And go Artemis.